Minecraft? For free? That typically costs quite a bit. I'll just go ahead and install it. This way, you might stumble across a suspicious Android app, and indeed, quite a bit of Android malware is being distributed this way, occasionally even via the Play Store. Welcome to the current chapter in the Practical Security Attacks lecture, and this time we're going to deal with Android reverse engineering. First of all, we'll look at how Android apps are structured, and in particular we'll look at the installers. We'll look at what entry points are, what is static analysis and what is dynamic analysis, two different kinds of code analysis, and we'll distinguish between top-down and bottom-up analysis. Finally, we'll look at some practical tools, for example, jadx. Here you'll find the learning goals. You know this, we'll skip it for now. Some people call reverse engineering an art. Now, why should you deal with reverse engineering? The goal of reverse engineering is to understand what a certain file does and how it does it. And this file could be an Android app, a Windows program, or some kind of operating system functionality, a piece of hardware, or any kind of mechanical or physical engine. And we'll try to find out how these man-made objects are constructed by deconstructing them and in order to reveal its design architecture. Now, it's certainly questionable whether this is an art, but it's probably because there is no recipe that works in all cases. Typically, we learn from experience which approaches indeed work best. And in this course, I'll try to teach you some of the basic principles and starting points, but I obviously can't teach you everything, and you will have to gather experience on your own. I would say reverse engineering is not really an art because it's not always beautiful. Let's look at an Android app. The input is typically an Android package, or short APK, and that's basically a zip file which contains the code, resources such as images, similar, and a manifest. And that reflects the basic structure of all the Android packages. Now, the goals for us in terms of reverse engineering is to understand what an app does from a high-level point of view, but we also want to understand the technical details on how an app actually does something. So basically, how is it implemented? And this could be done, for example, to find security vulnerabilities and then, to exploit them to gain some advantage. For example, to steal private information, to read private files, to steal its permissions, and something like that. All of that could be goals of reverse engineering. Looking at the structure of an Android app in more detail, so the structure of APK files, then we have a few points. First of all, we have the Android manifest, which lists the entry points, basically telling us where the code execution begins or can begin. And this also tells us a little bit about what we can expect from an Android app in terms of permissions, for example. Then there's two subdirectories called assets and res, which may contain resources, things like strings, binary blobs such as images, videos. Typically, this is not very important unless they are referenced in interesting ways, but they typically don't contain much code. with regard to these two subdirectories, you might want to quickly check for weird things, or for example, interesting ways of referencing these, but probably you don't want to lose too much time looking at these. The third element contains the bytecode, and that's in the file classes.dex. Potentially in further classes called classes2.dex, classes3.dex, and so on. And these contain the bytecode, and that is the juicy part of an Android app typically. Now, this is what you would typically feed into a disassembler or a decompiler in order to read the code. The result of this bytecode is typically compiled from Java or Kotlin source code. In addition to the bytecode, apps can also contain native code. And that means binary code that is specific to a certain architecture. And these come as so-called shared objects, so libraries basically. And they are typically compiled from C or C++ source code, so not from Java or Kotlin code. And typically these come in form of ELF files. The ELF file format is the file format for executable files in Unix-like operating systems. And this shows that Android is basically related to Linux, or that at the core it is a Linux-based operating system. And finally, we have some metadata, for example, the digital signature of an app. So all Android apps must be digitally signed and have certificate information. So basically, providing the identity of the author. Let's look at the Dalvik bytecode once again in terms of how the bytecode is generated. So we'll look at Dalvik bytecode in particular, and that is a little bit different than in the Java world, as you've seen in the previous lecture. The Dalvik bytecode is optimized for mobile environments, so smartphones basically. So typically you would write an Android app in Java or in Kotlin, that's the high-level language. So for example, it would look something like this. And then you use the Java compiler to generate Java bytecode. So this part, you know this from the last lecture. But now we're going to continue. And the next step is a dex compiler, which transforms the Java bytecode into Dalvik bytecode. And this Dalvik bytecode is contained in the classes.dex file, which is part of an Android APK. Now, on the smartphone, so on the Dalvik machine, basically, there's a Dalvik virtual machine which interprets or just-in-time compiles the Dalvik executable to machine code. Now we have a similar structure as with the Java world, except that we have the dex compiler in addition. Now, looking at the decompilation, we have a similar step. We try to revert from the Dalvik bytecode into high-level language. So the forward engineering, or in the forward engineering path, we can lose information. So we have the same problems as in the Java world. So the Dalvik bytecode is occasionally also called smelly code. We typically don't want to read smelly code, and instead we want to have it retranslated or decompiled back to high-level language code. So, and that is why we use a decompiler. If you look at Android apps today or nowadays, then in fact, app deployment on Android is slightly more complex. So the model that we looked at so far is slightly simplified, But the good news is that apps are still distributed as APK files. But if you have an Android smartphone, then you might have seen the screenshot that I'm showing here on the right. And that typically happens when you update the Android operating system. And what it does is it says it optimizes all the installed apps. And in the background, what it does here is it optimizes the DEX code, and basically it performs just-in-time compilation to machine code. So it kind of, you can think of this as converting the bytecode, the Dalvik bytecode, into machine code, because the apps can be executed in a faster way. We will not look at this in PRAX, however. So we will look at Dalvik bytecode decompiled to high-level language code, and that's pretty much it for PRAX. So feel free to forget about this for now, because we won't look at this. All right, this sounds great in theory, but how do we actually practically do reverse engineering, right? And so there's a few Android decompiler tools. Here's a few, I'll mention a few here. There are all-in-one products. For example, there's JEP, which is probably the best tool that you can get. It's a commercial tool, but there's a free demo version available. Then there's bytecode viewer, a pretty good one as well. jadx, which we will use in the lab sessions. And CFR is another Android decompiler. jadx is what we will use in the lab sessions. In theory, you can also use a Java decompiler by reverting the steps that I just showed. So from the Dalvik bytecode, you can try to recover Java bytecode using dex to jar, and afterwards you can decompile the Java bytecode into Java source code or Java pseudo source code. But that's typically not what you do. Now there's two different kinds of approaches in reverse engineering. And the first one is top-down. This is called top-down because you follow the execution flow through an app. And the basic question here is, where does the execution start? Or what are the entry points? Now think of this as an entry point is where the execution starts, and then there's a control flow which leads you to other nodes, which might be function calls, and you know, this way you kind of go deep into the code of an app, and you follow this from top downwards deep into the code of the app. So you start reverse engineering at the entry point of an app. So basically at the same point where the execution starts when the system invokes the code. And you can think of this as the main function or the equivalent of a main function in Java code. Now, in Android, there's multiple ways of starting an app. There's not a single main function, but probably something similar to the main function is the so-called main activity, and that is an excerpt from the Android manifest that you see here. So basically an XML or binary XML formatted file, which comes with every Android app. And here you see the definition of the main activity. So this is always in this clause, in this activity clause, and it's it has the name main activity in this case. And then there's two important aspects. One is the action tag in the intent filter. And this has to be set to Android intent action main. And the second one is the category, which has to be set to Android intent category launcher. And this basically tells the system that this activity should be triggered when the user taps on the icon of the app in order to start the app. Technically, the system calls the onCreate method of this class, and further methods are invoked from that point onwards. So there is no main function in the sense that we know it from Java. To summarize, the top-down approach means you follow the entry points, or you find the entry points, but we just looked at the main activity for now, but there are different entry points in the Android world as well, which could be services and broadcasts. And there's another option we'll look at later, but those are the most important entry points that you might want to look at when looking at an Android app. Probably the main activity is the most important though. However, occasionally the top-down approach may not always be the most efficient approach. For example, if you are trying to find functionality that is covered deep inside an Android app's code. So as a result, there's a second approach, which is called the bottom-up approach. This is called bottom-up because if we think of a similar control flow graph that we have looked at before, now we do not start at the top, so where the execution flow starts, but we look at some node deep inside the control flow graph. And from there, we'll backtrack up to higher nodes or upper nodes in this tree. And the interesting questions here are, how does the app, for example, interact with the environment? So for example, one analysis question you might ask yourself is, does the app communicate over the network? And if so, how? Does the app perform phone calls or does it send text messages? And that basically means you should remind yourself of the goal that you want to achieve. Typically, you try to find interesting Android API functions. Depending on your objective, for example, you try to find for methods that enable sending an SMS or a text message. And there's only so many so few ways basically to achieve that in Android, so that there's a few API functions. You need to research them, and then you can try to find where in the code these API functions are used. And once that's done, you can try to make a distinction, or you can basically state whether certain functionality was used or not. On this slide, you see the Android app components and in particular the entry points. In total, we have 4 types of app components, and these may serve as entry points. First one is an activity. The main activity is an example of that. Then we have services. So you can have an Android app run a service in the background. Think of this, for example, with a music player. Then obviously, even if you close the app, or if the app goes into the background, you want the music player to continue playing music. And that is, for example, typically implemented as a service. Then you have broadcast receivers. And that is basically used for apps to send and receive messages amongst each other. And the fourth is the content provider, which we'll not look at in detail in this lecture. Activities have a lifecycle, and we'll look at the activity lifecycle in a bit more detail. Typically, they start with the onCreate method that's being called. So basically, it's being called when the activity is instantiated. Then we have an onStart method, which makes the activity visible to the user as the app, prepares for the activity to enter the foreground and become interactive. And then the onResume method is called. Typically, that's the case when the app has been active and now re-enters the foreground. There's further methods, and we'll have a diagram showing you the full life cycle right here. So basically, the app transfers states in these, as shown in this diagram, and the boxes represent methods that are being called when transitioning from state to state. So it starts with onCreate, onStart, and onResume, which we've just seen, until the app is in the state activity running. And then there's the moment where the user basically wants to switch to a different app. Then the current app is being paused, or the onPause method is called. And once it's being put back into foreground, then the onResume is being called. So basically, think of these methods as being invoked as whenever the state of an app changes. So all of these methods serve as useful starting points for reverse engineering when following the top-down approach. So all of these methods might serve as entry points or triggering code execution in an app. It does make sense to familiarize at some point with the Android API, because the Android API provides lots of functionality. Typically, at some point, most, if not all apps use the Android API at some point. The Android API can be somewhat compared to the Java class library for Java, so it is well documented. Now here's an example. For example, if a sound file should be played using the media player class, then you basically instantiate the media player using the create method, and you pass a media file as argument by basically parsing a URI. Now in this case it's an org-vorbis sound file, and then you call the start method on the media player instance. Okay, time for some hands-on demo. We'll look at an Android app. Let's see what we can find out. We'll do this using jadx, which is one of the Java decompilers, and that's exactly the one you will use in the lab sessions as well. And first of all, we'll go ahead and open an APK and decompile its source. We'll open an APK that I have prepared. All right, we'll look at this sp_ntm APK. Now on the left-hand side, you will see a tree-like view. And this tree-like view will show you the elements of an APK file that we've learned about already. So if I open up this tree, then for example, you see the Android manifest. And if you click on this, jadx will show you a human-readable version of this XML formatted manifest. We'll look at this in a moment, but on the left-hand side, you will also see the source code tree. And as you can see, it has a packet structure that you already know from Java development. So you have packages, and then you have classes, and the classes have these green circles with a C. So in this part, you will find the classes and the code. Let's look at the Android manifest once again. So if you follow the top-down approach, what you would do is find the main activity, and we would find, or we would question ourselves, what activities are present, and in this part you will find the main activity. How do you know this? Well, basically you have the action and category tags in the intent filter, and you have the Android name. That is the class file of this activity. Now this is a relative class file, which you can find out due to the prefix, the dot prefix. Now the full name is the package name, which is given up here, followed by the class name main. So basically we have com.example.android.service.main. In addition, we have further activity, a second activity called receiver activity, and we also have a service defined, which is implemented in the class kitchen timer service. So basically we have at least 3 entry points that we can look at following the top-down approach. Now in addition, we have permissions which are provided in the manifest. And those are the app permissions, so what the app can be able to do or can be allowed to do. So in this case, we have 5 permissions which are stored. So for example, internet access, or getting the accounts that are configured on the system. And that is basically the set of permissions that an app can use during runtime. Okay, let's try to approach top-down. So basically we'll look at the main activity. So we go into the main class in the com.example Android service package. So here we see the code from the main activity. If we remind ourselves what the lifecycle of an activity, or what the lifecycle of an activity looked like, then we find the onCreate method, which is important because that is the one which is called when the activity is instantiated. So basically that would be the code that is run once this app is started. And as we can see here, as part of the onCreate method, a service is started, and this service is the kitchen timer service, which is in the same package. So basically you might want to switch over to that class and go deeper into that code. So you could proceed going top down by following and going into the kitchen timer service class. So basically it doesn't seem to do that much, so we can go back into the main class. But there's no single recipe that always works. So what we did now is going top down, but this does not guarantee that this might be the most efficient way for you to find out what an app does. For example, you could also go back to the manifest and check out one of the other activities. For example, the second activity that we have here, or you could go ahead and find out what the service does. Now, on the opposite, we have the bottom-up approach. Now, how would that work? And that would be completely different. So first of all, you would ignore what is provided in the manifest. Instead, you would try to find interesting code parts. For example, you could ask yourself, which kind of command and control communication, so what kind of network communication does this app? So we could open the search, the text search, and we could find for a word, for example, URI, for a term URI. And we wanted to, let's say we wanted to find this in methods, fields, code, and class. And we just go ahead and do the search. Okay. I just need to redo the search on the source, on the full source code. Here we go. Yeah. So in this case, the tool shows us 5 results. So we could just pick one of them. So the first, or the second line basically, and we could go ahead. And this would be somewhere deep in the code where the string URI would be found. And right here, what we see is that a class named URI would be used, and the parse method gets an argument, which is some kind of a URL. So this could be an interesting part in this app. We could look at what parameters are being concatenated to form the final URL, and also we could try to find out whether this URL is, being queried. So basically, what happens with this URL? And at this point, we are like deep in the code. We don't know how we reached this code, but what we could find nearby is that a similar URL seems to have been used a few lines below. And this is one or different way to navigate in the app. Okay, that should be enough for now. Let's go back to the slides. Obviously, you can try to repeat the same on your own. Okay. Now, in addition to top-down and bottom-up approaches, I'd like to highlight a difference in analysis techniques. And that is static code analysis and dynamic code analysis. Static code analysis means we do not execute the target code. So that's all that we've done so far would be static analysis. So if we use a decompiler and try to read code, then this is static analysis. In contrast, for dynamic analysis, we would execute the target code. Okay, and that's why it's called dynamic, because the target code is executed. Now, how would you do that? Well, you can use a real-world device, or you can use an emulator. Install the app in the emulator and then open the app. The static analysis tries to achieve or tries to infer code logic by deductive reasoning from the code. Okay, and in contrast with dynamic analysis, you would like to observe the behavior of the code. So you don't try to read the code, but you try to observe how the app behaves, what it does. Now, these terms are really important, and you should try to be able to use these terms in the correct way. Okay, so in terms of approaches, we have top down and bottom up. These are both approaches for reverse engineering. And in terms of analysis techniques, we have static analysis and dynamic analysis, while in static analysis, we do not execute the target code, and in dynamic analysis, we execute the target code. The dynamic analysis is not something that we'll do in PRAX. Let's summarize. Reverse engineering has or covers different strategies: top-down versus bottom-up, static versus dynamic analysis. We just learned about that. You should have understood the basic structure of an APK. So what is an APK? What is a manifest? What is DEX code? What is entry points? And you should know how an APK interacts with the execution environment. So bytecode is typically interacts with the Android API. And you should at least have heard about native code, so the code parts that are compiled from C and C++, and that those can do much more. We'll look at this last option, the native code part, in a later lecture. So for now, try to think about the bytecode and Android API. Now, there's a few more aspects that we have not looked at, but I hope that I've provided enough for you to get started in Android reverse engineering, and that's definitely something that you should do in the lab sessions. Now, most of the stuff that I've covered in this lecture is based on Yannick Fratantonio's MobiSec lecture. Yannick Fratantonio is a professor from Eurocom in southern France. In addition, I've used some material by Maddie Stone, who is a researcher with Google Project Zero. And she did an Android app reversing 101, and obviously the official Android developer information. That's it for now. Thanks for paying attention, and I'm looking forward to the live session with you guys.